Hi everyone, welcome to the lecture series on graph neural networks. In today's lecture, we will be exploring about a very fascinating type of graph neural network called temporal graph network or temporal graph neural networks, TGNs or TGNs. So, these temporal graph networks are designed to handle dynamic graphs or the graphs that evolve over time. Many real-world applications are dynamic in nature, which changes with respect to time. The nodes and the edges of the graph evolves with time. So let us see. My name is Aishwarya Nandakumar and welcome to the lecture. So let us get started. We will have a gentle introduction to temporal graph network. We will see what are static and dynamic graphs in this lecture. Then we will understand more about temporal graph network, which is a classification of dynamic graph. We will explore what are the modules of temporal graph network, how a temporal graph network works, and we will see the mathematical definition for each of the modules of temporal graph network. And finally, in the second part of this video, we will analyze temporal graph networks working with a very simple numerical example. So let us get started. Today our discussion will be mainly based on this paper published in Archive in 2020 titled Temporal Graph Networks for Deep Learning on Dynamic Graphs by Emmanuel Rossi and his colleagues from Twitter. In this paper they propose this temporal graph neural network which can handle dynamic graph. So initially we had static graphs which can work with graphs for different tasks like the node classification or edge prediction or the graph classification tasks. But the graph neural network can only train graphs which are static in nature, which means from the beginning of the training till the end, the number of nodes and edges remains fixed. It does not change with respect to time. Whereas in a dynamic graph, the nodes and edges evolve over time. At every instances of time, the nodes and edges can change. So many real-world applications like the social network interaction or the e-commerce platform, there are many applications where the nodes and edges evolve. So by using this temporal graph network, we can extend the deep learning to dynamic graphs by using graph neural networks. So the contribution of this paper is a memory module which can store the history or the information of nodes in every instances of time. So this is the GitHub repo of Twitter's TGN, which has got a huge number of stars and forks. So I found this paper very useful for learning temporal graph networks and graph neural networks. So now let us see what is a static graph and what is a dynamic graph. So at the top of this slide, you can see a static graph, and at the bottom, you can see a dynamic graph. So we are considering three instances of time. Initially t, and the next instance is t plus 1, and the next instance is t plus 2. So consider this static graph which you see on the top of this slide. At the instance t, the graph is having 5 nodes and 5 edges. Now in the next instance of time, which is t plus 1, again the number of nodes and edges of this graph is fixed. It is not changing. It has 5 nodes and 5 edges. It remains the same. And at the next instance also, the number of nodes and edges is not changing. It remains fixed. So a static graph is a graph where the nodes and edges are fixed. It does not change. New nodes are not added to the graph or the existing nodes are not deleted from the graph. And at the bottom you can see a dynamic graph. So in this dynamic graph, at the instance t, you can see there are 5 nodes and 5 edges. At the next instance of time, you can see here a new node is added to this network, which is represented by a slightly different color, and there is the addition of a new edge. So at the next instance of time, the structure of this graph changed. A new node is inserted into this graph. And at the next instance of time, which is t plus 2, you can see the formation of a new edge in this graph. So these dynamic graphs are the graphs that evolve over time. it changes. And we have many real world scenarios which are dynamic in nature. So we have to extend graph neural network to train on dynamic graphs, and we can use temporal graph network in such scenarios where the graph is dynamic in nature. Now let us see some examples for static graph. A very good example for a static graph is the network of roads in a city. Here you can see the map of a city where the intersections or the junctions is represented with this dot, red dot, and the roads that connect these intersections is marked with this black color. So the overall directions or the network of roads in a city remains the same. It does not change frequently. So here these red nodes can be considered as the nodes of this graph, and the black roads that connect these junctions or intersections can be considered as the edges of this graph. So here the nodes and edges are almost the same. It does not change with respect to time. So this is an example for a static graph. Now let us see the mathematical definition for a static graph. A static graph has fixed nodes and edges. Here you can see we have a source node I and a target node j. Here these nodes in a static graph are also associated with some features. This source node has a set of features and the destination node has a set of features. So here we denote these features by this vi and this vj, and where I is the source node and j is the destination or the target node, and eij is the edge that forms between the nodes I and j. So we know a graph neural network usually creates an embedding for the nodes. Here zi is the embedding. So here you can see zi is the embedding of this node. So how is this embedding created? We can basically think this as a message passing from I to j. So here the h and this msg are learnable functions, and mij is the message that is computed or the message that is passed from node I to node j. msg is the message function. This msg stands for this message. It generates a message from the features of the vertex or the node vi and its neighbor vj, and also the edge feature eij that connects the vertex I and j. Now this message function can be as simple as a linear transformation, and also this h is also a learnable function, and h is a function that aggregates the messages from all the neighbors of I and updates this node I's embedding. Zi is the embedding of node I. So what I wanted to convey in this slide is, you can see nowhere here we can see the dependence of time. This static graph is not dependent on time. It does not change. It has fixed nodes and edges that do not change with time. Now coming to a dynamic graph, here we have some examples for a dynamic graph. You can see here movie recommendation platforms. It is a very good example for a dynamic graph. When we enter a movie recommendation platform, when a new movie is added to that platform, we are shown recommendation for that. If that matches with our interest, then we are recommended with that movie. So our interest can change with respect to time. Maybe in 2019 I had an interest for a particular genre of movies. In 2024 it might have changed, but they will recommend us the content based on our changed interest. So how can they recommend the content with this new interest if they are not considering it as a dynamic graph? So this movie recommendation platform is a very good example for a dynamic graph. Similar is the pandemic graph. You can imagine a population where the people are represented as the nodes of a pandemic graph. The people can be susceptible, infected or recovered. So suppose we are creating our graph such that all the nodes, all the people in that city or that area is considered as the nodes of that graph. They are labeled as susceptible, infected or recovered people. Then this label can change. Initially, all the nodes can be susceptible people. Then when some of the population is infected with the disease, their label can be changed to infected. And at every instance of time, there will be interaction between the infected and the susceptible people. So at those instances, their labels can change, and at every instance of time, there will be an interaction between the people in that population. And once the people start getting recovered from the disease, their label will again change. At every instance of time, there are changes happening in a pandemic graph. So which is also a very good example for a dynamic graph. Next is the e-commerce platform where there are millions of users and items. These users and items interact with each other at every instance of time. There can be multiple events that can happen in an e-commerce platform. Like when I enter the platform, I logs into the platform. So that can be one event. I can view the items in the platform. This viewing can be one of the events which can have a label. Then when I add an item into the cart, it can be another event with another label. And when I finally proceed to the transaction, it can be another event. So at every instance of time, the users, the unique users will view the different items in that platform. So this viewing can be considered as the edge formation between the user and the item. And when we add the item into the cart, then it can be the change of label from viewing to adding the item into the cart and making the transaction. So at every instance of time, there are changes that happen into this e-commerce platform's graph. So this is also a good example for a dynamic graph. Similar is the case of a social network where there are many users and there can be multiple events like making friends with a person or posting something or mentioning another person. So this is also a good example for a dynamic graph. So here we can see we can have multiple or there are many scenarios where the graphs are dynamic in nature. So in many cases this dynamic event will be very crucial in this graph, so which needs to be considered. So we have to extend this graph neural network to handle these dynamic graphs. So temporal graph network with its memory module can train on dynamic graphs, and let us see how it is done. So as I said, a dynamic graph is a graph where at every instance of time there is a change happening. So here you can see at the time t equal to 0, there we have a fixed number of nodes and edges. Now at time t equal to t1, you can see there is an addition of a new node in this graph which is represented with this red color. So here you can see that, and at the next instance of time, this new node is interacting or it is forming an edge with another node. So there is the formation of this new edge. At t equal to 0, we do not have this edge. At t equal to 2, we have the formation of this new edge. And at time t equal to t3, the node gets updated in this graph. And at t equal to t4, the edge gets updated. So let us imagine this with the pandemic's example. At t equal to 0, we have a population which is represented by this graph where nobody is infected with the disease. So initially the whole population is susceptible to the disease. And at t equal to 1, a new person enters this population or a new person enters this graph. So he is infected with the disease, and now we have somebody who is infected with this disease in this graph. And at the next instance of time, this infected person interacts with a non-infected person. And at t equal to t3, this non-infected person gets infected with the disease. So it is a node update. And at t equal to t4, now here at t equal to t3, the initially infected person is now recovered from the disease, and at t equal to t4, the new infected person interacts with another non-infected person in this disease, in this network. So at every instance of time, there is an event happening in this network. So we can consider this dynamic graph as a series of time-stamped events. Now let me clarify one thing. There can be two types of dynamic graphs, which is called discrete time dynamic graph and continuous time dynamic graph. This is an example for a continuous time dynamic graph where the graph is considered as a series of time-stamped events. Whereas in a discrete time dynamic graph, it is simply the static graph that change, the static graph, different static graphs are stacked together, and when they are stacked together and we view that one by one, we will feel it is changing. So such a graph is called as a discrete time dynamic graph where the events are the snapshots of static graphs, whereas in a continuous time dynamic graph, it is the series of time-stamped events. So all these examples which I mentioned, like the ones that change continuously with respect to time, or at every instance of time there is a change happening, all these are examples of continuous time dynamic graph. Now let us see how a temporal graph network or a dynamic graph works. Coming to a dynamic graph's neural model, this can be considered as an encoder-decoder pair. Here the encoder is a function that maps a dynamic graph into its node embeddings. So this can be the node embedding of a dynamic graph. So the encoder takes as input a graph, a dynamic graph, and it creates the node embeddings for that graph, which are functions of time. And the input to this decoder is this node embedding created. So the decoder takes one or more node embeddings as the input, and by using that it performs the task specific things like the node classification or the edge prediction or the graph classification. So there are different tasks which we can perform by using a graph neural network. So how that works is basically it is an encoder-decoder pair where the encoder takes input the whole dynamic graph and it creates a node embedding from that, and this node embedding, by using this node embedding, the decoder performs various task specific functions like decoder performs various tasks like the node classification or edge prediction or the graph classification. Now let us see a simple example for computing the node embeddings. We have a graph with three vertices or nodes called named A, B and C. So this is a very simple graph with some initial features as 1, 0 for A, 0, 1 for B and 1, 1 for C. Now A is connected with B, B is connected with A and C is connected with B. Now let us see. Let us represent these initial features at time t equal to 0 as Va of 0 equal to 1, 0, Vb of 0 equal to 0, 1 and Vc of 0 equal to 1, 1. So these are the initial features of our graph. Now, if you have watched my previous lectures, in that I have explained very clearly what is message passing and message aggregation in a graph. Message passing and message aggregation are the main mechanisms in a graph neural network which we use in a graph neural network to perform various tasks. So let us see how we perform message passing and message aggregation in this simple graph. As I said, node A is connected with node B, node B is connected to nodes A and C, and node C is connected to node B. So by this message passing, all the nodes in this graph will pass its features to its neighboring nodes, and when these neighboring nodes receives these messages, it will use the received messages from its neighbor to aggregate the feature and update its feature. So here node A receives a message from node B, node B receives a message from nodes A and C, and node C receives a message from node B, and this message is the feature vector of these nodes. So this process of Passing its feature vector to its neighboring nodes is called as message passing. And here we use a simple mean aggregation for aggregating the messages. So let us see. Now for each node, let us aggregate the messages. So A received its feature vector from node B, B from A and C received its feature vector from node B. So the aggregated message for A becomes A got its message from B. So the feature vector of B is 0, 1. So now the aggregated message of A becomes 0, 1. Here we are using simple mean aggregation or simply taking the average of the received feature vectors. Now B received messages from nodes A and C. So now B received the features 1, 0 and 1, 1. So let us take the average of that. Whatever B received from vertex A and vertex C, let us calculate that and take the average. So it is the average of the feature vectors of A and C, which is 1 and 0.5. Now the aggregated message of B becomes 1 and 0.5. And finally C received its feature vector, or C received its message from node B. So finally now C received its feature vector from node B. So the aggregated message for C becomes what it received from node B, which is 0 and 1, 0, 1. So the updated or the aggregated messages of these three nodes becomes 0, 1, 1, 1, 1.5 and 0, 1. Now we can use a simple neural network layer or an activation function for further calculating the node embeddings, so that we will see when we do the numerical example for this part. Now let us see. Now the updated node embeddings are this. Now let us see what are the different core modules of temporal graph network. A temporal graph network mainly has 5 modules, which are memory module, message function, message aggregator, memory updater and embedding module. Now let us see what each of these modules are in detail. First one is the memory module. Memory module of TGN stores the information or the history of all events that happened in a node. Like, it stores the history of nodes in a compressed format. For example, you can see here we have a graph with 3 nodes A, B and C with its feature vectors. Now a new node is introduced in this graph. So when a new node is formed in this graph, it is considered as a new event and it is initialized with a 0 vector. Now whenever there is an event happening with this node I, like when this node I is interacting with another event or the label of this node I is changing, every event that involves this node I is stored in this memory module. So this memory module has the history of all the nodes in this graph and all the events that happened involving those nodes in the graph. So here Si of t is the memory state of node I at the instance time t. So whenever there is an event happening that involves this node I, this memory state of this node will change. And this memory module will have the history of all the changes that happened to this node I. Next module of TGN is the message function module. For each event involving node I, a message will be computed and based on that message, the memory of that node will be updated. So in a graph, there can be two types of events happening. Either an edge-wise event or an interaction event, which is the interaction of a source node I with a destination node j, forming an edge Eij, which will be an interaction event or an edge-wise event, and a node-wise event that involves the node. So Here you can see for an edgewise event, we can compute two messages. One message for this source node I and one message for this target node or the destination node J. Here, when we compute these messages, we will consider the previous time instance, which is t minus, and the current time instance, which is t. So, t minus is the memory of the Sj of t minus and Si of t minus are the memories of the nodes j and I at the time instance before the current time instance t. And Eij of t is the edge that is formed at this time instance t, and Mi of t is the message of node I, memory of node I at this Mi of t is the memory of node I at this time instance t, and Mj of t is the memory of node j at this time instance t. So it calculates this updated memory based on the previous interaction happened at the previous instance of time and the current instance of time. And for a node-wise event, it is also same. It will update its memory at the time instance t based on the previous instance of time. The event happened in the previous time and the current time. So these are the two types of events that can happen in a graph, edgewise event or a node-wise event. Now, the next module of this TGN is the message aggregator module. So, the purpose of this module is in a temporal graph network, or if we are using this TGN in a social media platform or an e-commerce platform or for any large graphs, we will handle those dynamic graphs as batches of events. For example, in our previous graph with 3 nodes, 1, 2 and 3, where at time t1 there is an interaction between the nodes 1 and 2. At time t2 there is an interaction between the nodes 2 and 3. So we consider this whole as a batch of events. Now we process these messages or these events as batches. So by doing this, there can be multiple events that involves the same node. So by aggregating the multiple messages of this same node and computing a single summarized message, we can handle these dynamic graphs. So we use an aggregation function for aggregating these messages. So we use this message aggregator module for processing multiple events that involves the same node in batches, and there are different ways for doing this message aggregation. One commonly used method is we will consider only the recent message of that node or the recent event that happened with that node and the mean of the messages happened so far till that time. So this is one method for calculating the aggregator message. Basically, the message aggregator combines the multiple messages of the node and creates a summarized single message. So here you can see Mi of t is the memory of node I at the instance time t, and agg is the aggregation function. What this aggregation function does is it takes a set of messages and it combines them into one single message. So Mi of t1, Mi of t2 and Mi of tb. These are the times of interactions up to the current time t. So either this aggregation function can calculate the mean of the messages computed so far, and it can convert these and it can create a summary of messages by calculating the mean of the messages and considering the recent message, or it can work as a recurrent neural network for computing the messages and converting them into a single summarized message. So by using this message aggregator module, we can process large graphs and we can batch process the messages and we can convert the events or the messages that involves the same node into one single message. Now, this is the next module of temporal graph network, which is the memory updater module. So, whenever there is an event happening in a node with a node, the memory module stores that as a list of events. So, for example, when a new node is introduced into a graph, it is considered as an event and it is stored as a list, stored in this list. And whenever more events happen involving this new node, it is stored as a list of events. So, this memory module knows the history of this node. It knows what all events these nodes are involved. So whenever an event involving this node occurs, the memory of that node will get updated, and we will use this updated memory for performing various tasks involving this node. So this memory updater is responsible for maintaining and updating the historical information of all the nodes in the graph. So by using this memory updater module, we can capture the long-term dependencies of this node which evolves over time. Whenever a new event happens, the node now remembers the new information along with the previous information. Now, let us see how this memory update, this process happens. So, here we have a graph with 3 nodes, and at time t, we have a new node introduced in this graph. So, Si of t is the memory state of node at time t. And m minus of t and Si of t minus, these are the memory states of this node at the previous instances of time. So, when an event happens at time t, now it generates a message for the node. So, what this message contains is the information of this node at this particular instance of time and the previous instances of time. And based on that, we update the memory of this node. So, whenever there is a new event happening, it will update the node's memory based on the current time and event at the current time and the events at the previous times. So by using this, we can analyze the behavior of this particular node. For example, if it is in an e-commerce platform, we can use this to predict the user's behavior in the e-commerce platform. If we are using this TGN in a some financial institutions projects, then we can use this memory update for analyzing the behavior of that user in making transactions or repaying the loan, etc. Now, coming to the final module, which is the embedding module in TGN. This embedding module can generate the temporal embedding Zi of t. Zi of t is the temporal embedding of node I at time t. So, why, like I said, this temporal graph network can be considered as an encoder-decoder pair, where the encoder will take the dynamic graph as the input and generate a node embedding. So this node embedding is a temporal embedding at time, at every instances of time. So the purpose of this embedding module in TGN is to solve the problem of memory staleness. So what is memory staleness? So, for example, imagine a social media platform with millions of users. So these users can log in to this social media platform at any time, and we can show them the content and we can recommend them with the ads that might influence them. But imagine this social media user, which can be considered as a node of this graph, becomes absent in this platform for a long period of time. So now this user or this node is not making any interactions with any other nodes in this graph. He is not interacting with other people or posting things or viewing things, which all can be the events that happens in this graph. So when this person logs back into the platform, he should be shown the ads or the recommendations based on uh, that particular time. So if it is after 5 years, he should be shown ads that might influence him after 5 years. So if this node is not making any interactions with the events, if the temporal embedding is not calculated for this node, then we cannot recommend him the personalized content at that time. But imagine we can compute the temporal embedding of this particular node based on the interactions of his friends or friends of friends. So if we can analyze those patterns and based on those interactions, like they were still making interactions or they were still forming edges with other nodes of the graph. So if this pattern, the whole pattern involving this person and his friends of friends, if that pattern is analyzed and a temporal embedding is calculated, then for this user who came back to the platform after a long period of time can be recommended with content at that particular time, which can match his interests. So this this embedding module can solve this problem of memory staleness, and there are many use cases which can. So there are many use cases where we can use temporal graph network with this embedding module and this memory module for recommending the content, for predicting the user item interaction, for foreseeing the market patterns, etc. So these are the different modules of a temporal graph network. Now let us see how we can combine all these modules and how this temporal graph network works. So as I said, we will consider the events happening as a batch of events. So now we have two time instances T1 and T2. There are three nodes in our graph, which is 1, 2 and 3. So at the time T1, node 1 is interacting with node 2 forming an edge, and at T2, node 2 is interacting with node 3 forming another edge. Now, the embedding module computes the node embeddings at this particular time instances. So here, the node embeddings formed are Z1 of T1, Z2 of T2, Z2 of. So the node embeddings computed are Z1 of T1, Z2 of T1, which are the node embeddings computed at time T1, Z2 of T2, Z3 of T2, which are the node embeddings computed at time T2. Now, this is how we calculate the probability of formation of edge between 1 and 2 and at time T1 and edges 2 and 3 at time T2. So these are the edge probabilities for this formation of these edges. Now we calculate the loss. So the messages are calculated by using the message function. So we have the messages like M1 of T1, M2 of T2, M2 of. Now we have the messages M1 of T1, M2 of T1, M2 of T2 and M3 of T2. By using the message aggregator, like I said, the function of this message aggregator is to aggregate the messages or aggregate the events happening with the same node and summarize it into a single message. Now the node 2, it has two messages. So it is aggregated with respect to that new time, and we have this aggregated messages as M1 of T1, M2 of T2 and M3 of T2. Now we update the memory of our node. Initially the memory will be of the previous instance of time. So now after aggregating this message, we update the memory. So the updated memory will become S1 of T1, which is the memory of node 1 at T1 time, S2 of T1, which is S2 of T2, which is the memory of node 2 at T2, and S3 of T2, which is the memory of node 3 at T2. So this is how a TGN uses all these modules, which are the memory module, message function, message aggregation, and memory updater module, and embedding module, to calculate the probability of formation of this edge. So by calculating the loss and by training this TGN, we can predict the probability of an edge formation between two nodes. So for example, suppose these nodes are the user and item in an e-commerce platform. If we can predict the formation of the edge between a user and item at a particular instance of time, then we can recommend them the ad and we can influence that user, or we can tell this user will buy this product at this particular instance of time. So if we can compute the probability of formation of edge at a particular time in a graph, then it is very useful, and this is how a TGN can do that. Now, in this lecture, we had a gentle introduction to temporal graph network. We learned what is a static and a dynamic graph. We explored the different modules of TGN. We analyzed the flow of operation of these modules in TGN and how a TGN works. And we also had a gentle introduction to the mathematical definition for all these modules in a temporal graph network. Now, let us see a very good numerical example for how TGN works, and it will be very useful in learning temporal graph networks.
Hi, in this part of the lecture, we will try to understand TGN or temporal graph networks through a numerical example. So we'll be assuming a small social media network with just 3 people who are users named as A, B, C, and we will try to predict the future interaction of a pair of users from this social media based on their past interactions, and we'll be using TGN for this. I'm Dr. Sridhat Panat. I'm a PhD from MIT, and in the rest of this lecture, we will be going through this very simple example by actually plugging in some numbers, and we'll be hand calculating the results of this TGN and the result of the prediction of the interaction between the users. So as you are already aware, in temporal graph networks, or in general in graph neural networks, we can use nodes for denoting these users, A, B, C, and the interactions between these users will be denoted using edges. So if you just go down, you can see how this interaction can be set up. So in this particular example, these 3 users are interacting at 3 different time points. At time point T1, the user A sends a message to B. So there is a messaging between A and B. At time point T2, B sends a message to C, and time point T3, A sends a message to C. So there are 3 users forming the 3 nodes of the graph neural network. And why is this a temporal graph network? Because the interactions are dependent on time. So the edges that are forming between 2 nodes will depend on what is the time point that you are looking at. Right? So that's why TGN is the perfect way to represent this dynamic graph. And what are the events or interactions which can form the edges between these nodes? They are these 3 events. We have one event at T1, another at T2, and another at T3. Now, let us keep a very well-defined goal where we want to predict after the time T3, what is the probability of A messaging B? So at time T3, A is messaging C, but we just want to see after T3, what is the probability with which A will message B? Or basically a messaging will happen between A and B. So that is our goal. So now let's proceed. Let's look at the steps involved in this whole numerical calculation. So in TGN, there is memory module, right? So we have to initialize the memory. Initially, there is no memory module. Initially, there is just the nodes and maybe the feature vector corresponding to those nodes. So we need to initialize the memory, and we have 3 events, each happening at T1, T2, and T3 respectively. And so we have to process those events. So these are the 2 main steps involved in our entire calculation. So let's look at memory initialization first. So each node or each user, we can start with a 0 memory. So we will assume that the feature vector is a 2-dimensional vector. So feature vector is technically not same as the memory that is stored in each of the nodes. So we will denote them separately. So far I have not shown you the feature vector yet, but the memory vector, which we denote as capital M underscore A or capital M underscore B, etc., is a two-dimensional vector because you can see two numbers here, and we will initialize this as a zero vector. Now, this first main step of initializing the memory is done. So now we will start processing the events happening at T1, T2, and T3. So first, let us look at the event happening at T1. What is the first event? In first event at T1, A messages B. The user A is messaging the user B, right? So during this event, there are three processings that we have to do as part of the TGN calculations. The three processings are computing the message. So this step, we can call it as in a formal sense as message computing. Then second is message aggregation. And third is memory updation. You might already be able to see that in message aggregation step, basically nothing is going to happen much because there are no messages to aggregate. There is only one message passing from A to B. B is not receiving messages from A and C at the same time, at least based on the example that we have taken. Which means you can already kind of see that the message aggregations step is not adding any extra burden on us, but it is one of the important steps involved in this processing. So we will show how it is done. And there is message computing before that. And after we aggregate the message, we update the memory. What do we mean by that? The memory that we initialized as the zero vector, 0, 0, you saw the two-dimensional vector. That was the original memory that we have to update based on what message is aggregating at each nodes during this time step. So now let's look at the first step, which is message computing. So message computing, we can represent using this equation. Don't worry if you are not able to understand this, I will make it very clear for you. So MSG is the short form for message. Capital M is the short form for memory. So MSG A underscore B means the message passing from A to B. So the nodes are bidirectional, right? You can pass message from A to B. You can also pass message from B to A. In this particular example, users can interact between each other. So we have to write, when we write the interaction between node A and node B, we have message from A to B and message also from B to A. So message from A to B is dependent on the memory of A at that particular time step, which is M underscore A, memory of B, and we have to also denote what time step this is happening at. Because in dynamic graphs, we also have to keep score of what is the time step at which this is happening. Only then we can kind of make sense of the temporal relationship between different nodes at different points of time. So initially the memory of node A is 0, 0, the two-dimensional vector, and memory of B is also 0, 0, and T1, which is the time step, it can be 0.1, 1 depending on what is your time step. And this operation, whatever we are denoting here, is concatenation operation. So at the end of it, when you concatenate these three values, so first one is MA, second is MB, and third is the T1, it will look like this array. So if T1 equal to, so if your time step is something like 0.1 seconds, it can be anything, right? So time step can be anything, but if T1 is equal to 0.1, then basically this value over here would be 0, 0, 0, 0, 0.1. This will be the result of this operation. And same thing goes here. So do you understand why both of these values look the same? Why this one and this one, why this and this look the same? It's because initially the memory at A and memory at B are the same thing. They are both 0, 0. So now if you try to calculate the message or compute the message from B to A, and it is dependent on MB, which is the memory at B, and then the memory at A, and time T1. And if you concatenate these three values, you get basically the same array. And that is only happening in the initial time step. This won't be the case in the future time steps, as you will see soon. The second step which we discussed. So we discussed 3 processing steps, right? One was message computing, second was message aggregation, and third was memory updation. So message computing is now done. So after we compute, we have these 2 messages. This is message from A to B, and this is from B to A. Next is message aggregation. So message aggregation will do nothing but it will aggregate all the messages coming into that particular node, but the message from A is going to B, message from B is going to A. Neither A nor B is receiving any messages from any other nodes. So there is nothing going to happen in the message aggregation. Otherwise, you can do an average. So if node B is receiving message from A as well as from C, then you can do an average of those 2 messages or any other type of message aggregation, whatever you want to use for your particular application. So this is the message aggregation step. Third step, which is a little bit to be explained, is the memory updation step. So just think about numerically what's happening in memory updation. Initially, we allocated the memory at node A and memory at node B as 0, 0 for both. In memory updation step, this 0, 0 should change to something else. And what is the basis with which it will change? It will change from whatever it was the previous value, and it will change based on what is the aggregated message to coming to each of these nodes. So this message is what is causing the change. So you can see that the M underscore A, this is the new memory at A, or updated memory at A. It is equal to GRU. GRU is a function. I will come to that in a moment to explain what exactly does this function do. But there are 2 parameters going into this function. One is the aggregated message at A that we calculated over here. Let me make myself a bit smaller. So you have the aggregated message at A, right? So that is one of the arguments going into this function. I'll just map it here. The second argument is the previous or the initial memory at A. This is the updated memory. MA over on the left hand side is the updated memory. And this MA is the initial memory. So the updated memory of A is a function of 2 arguments, aggregated message at A and the previous or initial memory at A. Now let's look at what is this GRU function. But just before that, I just want to show you the whole array based notation of this. So it is GRU of the aggregated message here is 0, 0, 0, 0, T1. Right? The initial memory at A was 0, 0. You saw that from the previous step. And for the memory at B, the updated memory at B is a function of aggregated message at A and the original memory at B. Sorry, the aggregated message at B and the original memory at B. And we perform this GRU function. Now let's come to what exactly is this GRU function. GRU function is called as gated recurrent unit, GRU. It's a type of recurrent neural network that can handle sequential data, and it can help us capture long-term time-based dependencies. And as you saw, GRU function takes 2 inputs or 2 arguments. One is the aggregated message at that particular node. The second is the previous memory state. Using these 2 things, it will calculate the updated memory state. The updated memory state or new memory state, right? This is the purpose of this GRU function. Okay, now some more details about this GRU function. I just want to show you an example of this, although I don't want to go into the entire details of the architecture of this GRU function because that will be a little bit out of scope of this lecture. I just want to give you a flavor of this GRU function calculation. So MA updated equal to GRU of aggregated message at A, previous memory at A, and that is equal to this. So here I am assuming that T1, the time equal to 1. If it is 0.1, this was 0.1, you can assume whatever, it depends on your particular calculation. But if this was 0.1, this guy instead of 1, it will be 0.1, right? This value. And same here, this will also be 0.1. So this depends on your time step that you have in your particular system. But the GRU has these following units. It has an update gate, a reset gate, candidate memory, and final memory state. I don't want to bombard you with a bunch of these terms, and I don't want you to get confused where we are headed. So just before going into the details of these four things, we were assuming a simple social media network with three people. These three people were interacting with each other at different time points. And our goal is, based on these interactions at the past time points, can we predict a probability of interaction between two of those people at a future time point? That is our goal. So we started with memory allocation. We initialized the memory at each node as 0, 0. Then at each time step, we are doing three operations. One is message calculation, message aggregation, and memory updation. Right now, we are in the memory updation stage. And in the memory updation, we use a function called GRU, gated recurrent unit. And the GRU function consists of these four items. I don't want to go into too much details, but I'll just show you what exactly this is. Sigma, if you are familiar with neural networks, this notation you might be familiar with. W is like a weight matrix. Weight, right? Sigma, you can imagine it's like an activation function. And this is the input. So this input, you can see over here, this guy, the concatenated value. And what the update gate does is it determines how much of the past memory to keep. So in the previous time step, if the memory was something, this will decide how much of it to keep. The reset gate, which is another weight matrix, it's exactly the same. So this initial function and the update gate function and the reset gate function looks exactly the same, right? Do you see any difference? The only difference is probably in the weight matrix value. So this is WZ, this is WR. And other than that, it's exactly the same. Then you have a new memory state that is calculated based on RT, which is the reset gate output, RT over here, and the weight corresponding to this candidate memory. So, and then the final memory state is almost like a weighted average of the previous memory state and this candidate memory state. So HT minus 1 is the previous memory, HT is the potential new memory state, and the new final memory state is like a weighted average. The weights are these two terms. I am fully aware that at this point, maybe you are a little bit lost. I don't want you to focus too much on these functions. While creating this lecture, I originally thought maybe I'll remove this portion. I'll just say GRU is a function which acts like a recurrent neural network, and it has weights and activation functions, and it produces an output. But then I thought maybe I'll just show you the function just in case. So I don't want you to pause the lecture right now or drop off from it, because it's only going to get easier from here. So just don't worry, just stay with me. So as I mentioned, the WZ, WR, and W, these are all weight matrices. They all can be, for simplicity, they all can be the same values. The numerical values of these three weight matrices could be the same. Sigma is the sigmoid activation function. Tan hyperbolic, it's the tan hyperbolic activation function. And this is the concatenation of previous memory state and the input, which you can see over here. Which you can see over here. Yeah, this one. Okay. Now, we'll come back to our business. We'll just come back to the GRU output. So what we will assume is that in this particular example, the output of GRU is equal to 0.1 and 0.1. So what is the logic of this? The logic of this will be clear when you make a calculation based on certain assumed values of this weight matrices. And when you plug in the numbers, what are the numbers? These are the input numbers, which are arguments into the GRU function. So if you make a calculation, depending on the values of W, WR, and WZ, you will arrive at GRU output. So GRU of, let's say there are two arguments, right? Argument 1 and argument 2. You will get some output. In this particular case, the argument for GRU for node A as well as the GRU for node B, they are exactly the same, because the message aggregation is the same for both. The original memory at both of the nodes A and B were also the same. So the GRU of node A will be same as GRU of node B in this particular time step of node B. and we can calculate it depending on the values of weight matrices. So let's assume that the output of this is 0.1, 0.1. You might be frustrated with this at this point. Where am I pulling this 0.1 and 0.1 from? The values will heavily depend on what is our choice of this weight matrix. So I don't want to bore you with a lot of numerical calculations where I'm multiplying this weight matrix with the input and then performing activation function and doing it 2 or 3 times before I reach this output. Just bear with me. Just assume that the output of this GRU function, which is the gated recurrent unit function, is 0.1, 0.1. Now this is what? This is the updated memory. The output of the GRU function is assigned as the updated memory, right? So now let's come back to the nodes. Now the nodes, we had 3 nodes, right? A, B, and C. You can see that the updated memory of C is same as before. Can you guess why is this the case? This happened because only A and B interacted in this particular time step T1. C was not part of the interaction. So the memory of C did not change. But memory of A and memory of B, both of them changed to 0.1, 0.1 because they interacted. The interaction led to message function calculation, which led to message aggregation, which led to memory updation. Memory updation was done using the GRU function. And as a result of that, now we have updated values of memory for A and B. Now, please remember, these memory values are not the same as the node embedding or the feature vector. Memory is different from that. Although, in certain cases, for simplicity, we will say that the memory value itself represents the vector embeddings of the features. But we will come to that in a moment. So, what we did so far we covered the first event. What was the first event? The event that happened at time step T1, where the user A messaged user B. This is the event that happened at T1. Now we move on to the next event that happens at time step T2. What happens at this time? At this time, the user B messages user C. There is no interaction between A and C, or there is no interaction between A and B at this time step. Now again, because an event happened at this time step, we have to do 3 processings. If you remember, message computing, message aggregation, and memory updation. So let us do these 3 steps in time step T2. First is message computing. In message computing, this time the messaging is happening between B and C. So the first one is MSG underscore B underscore C. MSG for message. Underscore B underscore C means the messaging is from B to C. And if we are computing the message from B to C, we should also compute from C to B, because in these nodes, there are bidirectional interactions, or there can be bidirectional interactions. So MSG underscore B underscore C is dependent on memory of B at that particular time step, memory of C at the time step, and we also take a note of the value of the time step T2. And what we do is we concatenate these arrays, and finally we get the final array 0.1, 0.1, 0, 0, T2. Why is this 0.1, 0.1? Because if you remember from the previous time step, the MB got updated. MB was originally 0, 0, but it got updated to 0.1, 0.1, right? So that is why you see this value here. And now you will be a bit happy to see that the MSGB underscore C is not the same as MSGC underscore B, because the message from B to C is looking like this guy, but message from C to B is looking like this. Previously, it was just 0, 0, 0, 0, T1, right? Now, if T2 is 0.2, you can replace T2 with that number. But this is the message passing between A and B, the computed message. Next, we do the second step. What's the second step? Message aggregation. Again, nothing special happens in message aggregation here, because the only 2 nodes involved in message passing over here is B and C at this time step. B is only receiving message from C, or C is only receiving message from B. There is no message reception to B from A. So you don't have to do anything special to aggregate. The message aggregation is same as the computed message. If there was message coming from other nodes, you may have to take an average or whatever mathematical operation you are doing to aggregate the message. So this is the aggregated message. Now you might be ready to guess the next step, memory updation. Now this time, which memories are being updated? The memories of B and C. A is not involved because A is not part of the messaging in this particular time step. So now in memory updation, the updated memory of B, so this is updated, right? I'll just write it here. Updated memory of B, which is updated memory of B, is a function of the aggregated message at B and the initial memory at MB. So here, when I say initial, I don't mean the original 0th time step. I mean whatever it was just before this time step. So this MB will not be 0, 0. Rather, this will be 0.1, 0.1. So please note that, right? Because in the just previous time step, this MB had changed. So that is what we have to use here. And GRU is the gated recurrent unit function. For MC, it will be the GRU of aggregated message at C and the memory at C. Memory at C is actually 0, 0. Why? Because C was not involved in the previous time step. So C memories of the C was same as whatever we originally assigned. So now the GRU function will be GRU of this guy 0.1, 0.1, 00 T2. And the MB, as I mentioned, it's 0.1, 0.1 over here. And here it's 0, 0. And the aggregated message is 0, 0, 0.1, 0.1. Where is this coming from? This is the aggregated message. If I zoom out a little bit, this aggregated message is coming here. This aggregated message is going here. This whole thing and this whole thing, right? And these were the previous memory values just before this current memory updation step. And after memory updation, this will become this whole term will be the new MB and this whole term would be the new MC. So in the memory updation step, we have new memories for these two nodes and memory of A is not changing. So now after this event T2, this is what happens to the node memory. The node memory at A was same as whatever it was in the just previous step. So it remained 0.1, 0.1, but memory of B got updated to 0.2, 0.2 as you see here, and memory of C got updated to 0.05, 0.05. One small thing to mention here is you might be wondering again, where did I get these two set of values from, like these two guys? I got it from assuming a certain weight matrices for the GRU, gated recurrent unit. I'm not showing this calculation to you, so please don't feel frustrated that you're not really understanding where these exact numbers came from. Just assume that if the gated recurrent unit setup has certain weights, then we can calculate these updated MB and MC values. Okay, so we also did the processing for time step T3. Now we go to the last T2. Now we go to the last time step T3. In T3, B has no role to play. A and C interact. A sends a message to C. That's what's happening at T3. Again, we do three things, right? We do three processings: message computing, message aggregation, and memory updation. In message computing, this time we are computing the message from A to C and C to A. B is not involved. And here, A to C, message from A to C is dependent on the memory of A, memory of C, and T3. Memory of A, which memory of A are we taking? The memory of A from the just previous step. That is this. Memory of C from the just previous step. And same here. Memory of C and memory of A. And then T3. T3 could be 0.3. It could be 3, depending on whatever is your time step. So this is the message calculation or calculated message. Now, as you already guessed, the aggregated message at A and aggregated message at C are same as these two values respectively. This is this and this is this. Why? Because only A is messaging to C. There are no other nodes involved in messaging to C. Only C is messaging to A. So A is only receiving message from C and C is only receiving message from A. There is nothing to aggregate. In memory updation, this time we update the nodes A and C. B is not involved because B is not involved in this particular time step in any kind of interaction. So we again use gated recurrent unit. We have aggregated message at A and the previous memory at A for calculating the updated memory at A. The previous memory at A was what? The previous memory at A was 0.1, 0.1, right? This was the previous memory. So we'll have to use this. The previous memory at C, if I remember correctly, was 0.05, 0.05. So this is the A and C. Aggregated message is this guy for A and this guy for C. Okay. Now we calculate the gated recurrent unit function output. And these are the two inputs, right? Aggregated message at A, aggregated message at C, previous value of memory at A and previous value of memory at C. To get the updated value of memory at A, M underscore A, and updated value of memory at C, M underscore C. Again, I will repeat. The reason why these numbers popped out of nowhere is because I assumed certain weights for the underlying functions or underlying calculations for the gated recurrent unit. I am not showing it to you because I don't want to complicate this lecture, but just trust me, these are the values for M underscore A and M underscore B, which is obtained after the memory updation step. So now what does the memory look like for these three nodes? After the event of T3, this is how the entire node memory looks like. The A has this value 0.25, 0.25. B has 0.2, 0.2, and C has 0.15, 0.15. I think we are very, very close to wrapping up, meaning we are very close to now computing the probability of interaction between A and B now, because that's what our goal was. Our goal was after the event T3, what is the probability of interaction between A and B, right? So we'll come to that. So we are almost there. So just before we compute the probability of interaction between A and B, we have to calculate node embeddings. What is node embeddings? Each nodes have features. So let's say this is the person A and this is person B and this is person C. Each person has features. Let's say age, let's say gender, then maybe income. Whatever info these social medias are having from us, this can be represented as a vector, right? 56, male, whatever, then income, $3,600 per month, whatever. So each of these people have these features. These features are represented as a feature vector, and that form a crucial part of the node embedding. In our particular, so usually you have to do a certain processing, or you have to pass this message at A through a certain function to produce the node embedding. In our particular example though, we will take it very simply. There is a one-to-one linear mapping from MA to ZA. So ZA is the node embedding. So ZI is the node embedding of, is the embedding of ith node. So ZA is the embedding of A node, the node A. And we'll say that it is exactly same as the memory at A, right? And memory at A was 0.25, 0.25. So that is the node embedding of A. Then for ZB, it is same as the memory at B. And for ZC, which is the node embedding at C, that is the same as memory at C. So these are the node embeddings. So now we have the three node embeddings for the three nodes A, B, and C. Now we are finally ready to calculate the probability of interaction between A and C given these three node embedding values at this point of time. So what we do is, let's take a pause. Our goal was to predict the probability of interaction between A and B after time T3, right? Can you have a look at this and see what is common between A and B, or rather how similar it looks? So let's say there is a person A and person B on social media whose preferences, whose age, whose income, whose gender, everything is similar. And they are also connected like in a network, like they are friends. Then there is a very high chance of interaction between them, right? There is definitely more chance of interaction between those two people who are like-minded than two people who have completely different interests and who are completely different age groups. So here you can see that this feature vector or this node embedding 0.25, 0.25 is looking kind of similar to this feature vector, which is 0.2, 0.2. So maybe intuitively you can predict that, yeah, there is probably greater than 50% chance of interaction between these two guys, because at this, my pen did not come, greater than 50% interaction between this A and B at this point of time, because at this point of time, if you look at the value of the node embedding, those vectors are looking very similar. right? So maybe intuitively you could make such a statement, whereas A and C do not look that close. They are a bit different. The feature vector of A and C, are the node embedding of A and C, look slightly different, right? This is 0.15, this is 0.25. So that could be your intuition based on no calculation. So let's see how we can do the same thing based on calculations. Now, the very last step in this TGN is making the prediction as a probability. And for that, we use something called as multi-layer perceptron, MLP. What is MLP? Is it something, something that you should not know? No, it's very simple as a neural network. It's literally a neural network. Neural network. So that is MLP. And multi-layer perceptron, you will come across this terminology in many contexts. So whenever you see that, don't just get worried. It's very as simple as a neural network. There are some nuances, but I don't want to go into that. So we'll try to predict if A will send a message to B after time step T3, after all the initial 3 interactions. And for this, we will use an MLP. So to this MLP, we have to give certain inputs, right? So the inputs will be the node embedding of A and node embedding of B, because we are trying to predict the interaction between these two guys. So C is not involved, so we don't need this node embedding. So the MLP, which is the neural network, we will assume that there is only one hidden layer, and we use sigmoid activation at the output. So I will show you the structure of this neural network so that you can visualize it. So this multi-layer perceptron will take some input, right? So let me first show you the input. So the input involves this ZA and ZB concatenated into a single array of dimension 1/4. So the dimension of this is 1/4. And so this is ZA was 0.25, 0.25. So that is the first 2 terms of this array. ZB was 0.2, 0.2. That is this. And now this input we will be feeding into the input layer of the multi-layer perceptron. So this 0.25, 0.25, 0.2, 0.2, we are feeding into the multi-layer perceptron. So first, before you look at any of this, just see that this is the input layer. So the input layer has 4 nodes. This is the hidden layer. This has 2 nodes or 2 neurons. And this is the output. In the output, we also have a sigmoid activation function. Okay. Now I have written a few numbers here. I'll come to that in a moment. So basically the input we are feeding element wise. So 0.25 is fed to the first node, 0.25 to this node, then this 0.2 to this node, and this 0.2 to the last node. And we have a kind of a fully connected neural network here. So all neurons in the previous layer is connected to all neurons in the subsequent layer. So here this particular node is connected with this and this. This is connected with this and this. So you can see there is white color arrow going from this node to both of the nodes in the next hidden layer, yellow arrow, pink and blue. And this 0.1, 0.5, 0.2, 0.6, these are the weights of these connections. So you can see that since there are 8 connections, there are 8 weights. You can represent these weights as a matrix of dimension 2/4. So it could be something like this. 0.1, this will be 0.5, this will be 0.2, this will be 0.6, and 0.3, 0.7, 0.4, 0.8. So this weight matrix is represented as the connections between the neurons in the input layer and hidden layer. Now, in the hidden layer, we are getting inputs from the input layer, and there is also a bias for each of the units in the hidden layer. There is 0.1 as the bias. So bias is added. So what happens here is, here in this node, we will have sigma wx, and then you add the bias to it. So bias is 0.1, w is each of these values, and x is the input. And that is happening at both of these nodes in the hidden layer. And then here again, there is fully connected neural network. So hidden layer, both nodes of the hidden layer are connected with the output layer. And the weights are 0.2 and 0.3. And the bias is 0.1. And then whatever is the output you obtain here after doing this calculation is passed through a sigmoid function. And then at the end of it, you can calculate the output. So if these are the weights, whatever you see over here are the weights, and whatever you see here are the biases. And if these are the inputs, you can calculate the final output to be 0.59. And as you know, sigmoid function can output a value between 0 and 1, and this 0.59 is a probability. So what does this mean? It means that after time t3, there is a 59% chance of interaction between user A and user B in this super tiny small neural network, right? So that is basically where we are at the end. So there is a 0.59 probability after time 3 between these two guys to interact. And we got this probability at as the output of the multi-layer perceptron. And you can repeat the same steps for after processing the events happening. Let's say you had time steps from T1 all the way till T10. You can repeat whatever we did until that point, and you can calculate a probability at basically any point of time. So this numerical example, I hope, gives you at least some, not intuition, but at least some, it throws some light into the numerical details involved in the calculation of user interaction prediction in social networks. I am fully aware that the example that I have chosen is something that is oversimplified. And because we are hand calculating, of course, I had to make a lot of oversimplifications. Otherwise, it will not be easy for me to do it on a blackboard. But I hope you got a fairly good idea on how this works. And we will come with more interesting examples and code-based implementation of TGN and other dynamic graph networks in the subsequent lecture. And until then, please take care and see you soon. Bye.